go back and analyze the idea of over and underestimates when it comes to the trapezoidal and midpoint rules. And we said that intuitively it seems to depend on the bend of the curve, how it bends, so how its curvature is. In other words, its concavity as well. We know that the error bound had to do with something with the second derivative, which is related to concavity. So let's go analyze some shapes, looking at them with the midpoint rule and the trapezoidal rule. So let's start with just flat functions, which are basically just lines, and see what will happen when we use midpoint or trapezoidal to approximate the area under lines. So let's say we have this function f of x, and we want to approximate it using the midpoint rule. I'm going to, instead of cutting this into subdivisions, let's just look at one giant interval, and things will become pretty clear. If I go to the midpoint of this one giant interval between a and b, right smack in the middle, and make a little rectangle, notice what happens. As much as it goes over, because this is a line, it goes that same amount. These are two congruent shapes. It goes that same amount under. So here it goes under, but by the exact same amount it goes over. Therefore, for a linear function, we have the midpoint rule having an exact answer. It's an exact approximation. In other words, it's not an approximation. For linear functions, the midpoint rule will be exact. It won't have any error. Now let's look at the trapezoidal rule. That's pretty clear, as you can see. I'm going to look at this one giant interval, and I'm not even going to bother cutting into sub-intervals. Here's my left endpoint. Here's my right endpoint. I'm going to make a trapezoid out of that. And what happens when I make a trapezoid out of that? I don't go over or under at all, and again, the trapezoidal rule happens to be exact for linear functions as well. So now let's look at curves for both cases. We're going to look at curves that are, let's say, concave down, and then we're going to look at curves that are concave up, and we're going to analyze by looking at maybe one giant segment to see what happens. Let's look at the trapezoidal rule first. That might be a little bit easier to analyze. Let's say I have a curve that looks like concave down, so something like this. That's my f of x. Let's look at it from A to B. And if I'm just looking at that one giant interval, and I want to approximate it with the trapezoidal rule, I would look at this endpoint and this endpoint, and I would make a trapezoid out of it and look at that area. Now that's pretty clear. I'm missing all the stuff up above, so it looks like for something that's concave down, the trapezoidal rule is going to be an underestimate. So trapezoidal for a concave down curve clearly is going to be an underestimate, because it's going to miss all those little regions. Even if I make more subdivisions, it's going to miss them. Concave down curve, so let's say it's concave down, and I'm going to use the left and the right endpoints to make my trapezoid. Oh, we did concave down. I meant concave up. So now if I look at a function that's concave up, and I focus on one giant segment from A to B, I'm going to use the left and the right endpoints to make a trapezoid, and notice clearly what happens when I make a trapezoid in that one giant interval. It's going to end up being an overestimate. So when I'm looking at the trapezoidal rule for concave down curves, for those pieces I'm going to have an underestimate. For concave up curves I'm going to have an overestimate. Granted, your curve can change, become concave up and down throughout the process, and you just pay attention to what's going on in each case. Now let's go look at the midpoint rule. Let's say this is my function, and I'm looking at one giant interval, and I'm going to take, of course, the midpoint of that interval to get my little height or little length, whatever you want to call it, and then that's going to be the area in between. Notice for this case, it seems like I went over more than I went under. I can kind of tell that from the way it's drawn. However, there's an over and under going on, and depending on how this rises or how it curves, things could change. So if we can't really clearly tell, what we can do here is another little trick. So this is the area in red that the midpoint rule approximates. If we take a tangent line at that midpoint and we look at what we ended up here with, what we were using to make the midpoint, this area and this area are both congruent. So if we make a tangent line right at that midpoint with this other horizontal line that created the length or the height of our midpoint rule, we're going to have two congruent triangles that have the same area. So using this rectangle to get the area of the midpoint is basically the same way as if I were to erase, since these two are congruent right here, if I were to erase this blue portion and say I'm going to keep that top triangle piece to figure out the area using the midpoint rule. So in other words, what you're doing is, instead of using the rectangle, you're using the congruent triangles to figure out what the area would be with this trapezoidal looking thing, which is not the same trapezoid as the trapezoidal rule, because there you would be using this point and this point to make a trapezoid. Notice that would be an underestimate if you were using the trapezoidal rule. Here this is just a little trick to say that this new trapezoid that I've made actually has the same area as that rectangle I had made with the midpoint rule. So if I do it that way, then notice that clearly the midpoint in the concave down version is actually an overestimate, because it goes a little bit over here and a little bit over here as well. So this is going to be an overestimate. So the midpoint rule for concave down curves is actually an overestimate. Similarly, we can see the same thing for concave up curve. So we're going to go look at this concave up function. We're going to look at one giant interval of approximating using the midpoint. I'm going to go in the middle of it and make my rectangle, and this is the area that my midpoint rectangle uses to approximate. I'm going a little over in this case, a little bit under in this case. It looks like they're pretty close, they may even each other out. And if I use this idea of, okay, let me make a tangent line through that midpoint. And if I make that tangent line, this triangle and this triangle will be congruent. So instead of using this portion right here, I'm going to get rid of this and only use that. And if I do that, I'm going to actually end up with looks like an underestimate in this case. My eraser is not working as well as I would like it to be. So if I'm using this trapezoid, the blue portion is the top of my trapezoid. Now if I'm using this trapezoid that supposedly is equivalent based on the congruent triangles, equivalent to the area of that rectangle I had created, notice I'm going under in each cases, so the midpoint rule will be an underestimate. So overall, recap. Let's go back up. If we're dealing with lines, both midpoint and trapezoidal rule will give us exact values. There isn't going to be any error. If we're looking at curves, for concave down, underestimate for trapezoidal, concave up, overestimate for trapezoidal. If we're looking at the midpoint rule, concave down, overestimate for the midpoint rule, concave up, underestimate for the midpoint rule. So these two behave, it looks like, in the opposite way that these two do. This for concave down was an underestimate, whereas in this case it was an overestimate. So looking at that and keeping that in mind also, it gives you an idea of how off you will be when you look at a graph, let's say, and try to analyze using the two methods.